Just as an introduction, as we're kind of settling down, this panel is made up of Maria Silveira, who's with the Institute of Food and Agricultural Services with the University of Florida. We have Edie Witter. I know a lot of you know her. She is the president of ORCA up in Fort Pierce. She's she actually, remember those Michelin Man dive suits that you used to see on TV? She used to go in those things and go down in the water, and she actually broke the depth record one time, went down over 2,000 feet down in the ocean, and she said she could hear crackling and stuff around her suit, but that's not what bothered her. What bothered her is the big thing that swam right next to her while she was down there. And then we also have Tony Janicki, as well as Del Botcher. They have been around, they got probably a combined age in doing nutrients in surface waters of Florida for over 80 years, probably between the two of them. And they are the go-to people, third parties, when you are looking for anything about nutrient loadings in the surface waters. Harvey Harper, well, we'd like to have had him here also today, but he was unable to attend. But we've got a premier group here to talk about what you've just learned about. I think we all know about biosolids now, and we probably don't need any more definitions of it. And so let's just get started first. One of the things that was being brought up before was the issue of phosphorus. And we're all concerned about phosphorus. And we're going to start with Maria, just to explain us a little bit about the fertilizer recommendations overall in pastures in Florida, and a little bit of the issues relative to the difference of phosphorus solubility and availability, and also some of the limitations associated with some of the testing of phosphorus that's used in the nutrient management plans.
Thank you, Gary. Good morning, everyone. My name is Maria Silveira. I'm Associate Professor in Soil and Water Science at University of Florida. I've been working with biosolids since my PhD. Believe it or not, I enjoy working with biosolids, which is hard to believe. But today I'm here to cover three main topics during this very brief presentation. I want to touch base in. So here's the purpose of my presentation. I want to talk about, demystify some of the issues related to fertilizer recommendations for pastures. I work primarily with beef cattle producers. Sometimes we have the idea that they are using as much fertilizer as they can, but in reality is a little different. Then we're going to talk about differences in phosphorus solubility among different phosphorus sources, including biosolids, but also other sources that are equally important in terms of causing environmental problems. And then we're going to talk about ways to access environmental hazard, whether or not soil test is a good indicator or not. So the first topic, and you understand why they are interrelated. I keep forgetting. Okay. This is the document that dictates fertilizer recommendations, nitrogen, phosphorus, potassium, recommendations for agronomic crops. So even though this document doesn't have any regulatory purpose, we know that the regulatory agencies are using this document to define best management practices associated with different agricultural enterprises. And very briefly, I have to provide you a little bit of a historic perspective, because this is an evolving document. It has gone through several revisions every time that we have new science, and it's a science-based document. So we are putting aside all our perception, our feelings, which is sometimes is very hard to do that when we're talking about biosolids. There's a lot of public perception. So I'm here to represent science, not any other entity, not agriculture, not environmental groups. I'm here to show you what, in terms of science, what we know as of now relative to biosolids. So when a producer is enrolled in a BMP program, or they submit a soil sample to the Extension Soil Test Lab, the fertilizer recommendations are going to be based in this document. And usually our fertilizer recommendations, most universities are much more conservative compared to, let's say, a commercial lab. The reason for that is because in Florida, we have different fertilizer philosophies versus some people in the Corn Belt, for instance. We have very poor soils with very limited nutrient holding capacity, so we cannot afford to apply too much fertilizer. The goal is not the soil, the goal when we apply fertilizer is the crop. I'm gonna focus on the Bahia grass. Bahia grass is the predominant forage species, so the cow-calf industry, the beef cattle industry relies heavily on this grass. And this grass, phosphorus recommendation for this grass has gone tremendous change in the past 11 years. I was hired in this position in 2006. If somebody can please, yes. And this is just very briefly, the historic perspective. In 1996, Central and South Florida didn't have, University of Florida didn't recommend soil testing, which basically left, if you read that, the red letters, there is no, soil test is not a reliable tool to guide pasture fertilization, Bahia grass, which 90% of the beef cattle producers in Florida have. So therefore, fertilizer decisions should be based on the economics. That left an extremely large room for error, either way, either over-applying or under-applying. So when I was hired in 2006, a group of folks from university and some state agencies got together and said, we gotta make this recommendation better. So in 2007, we implemented this new change. From 2007 up to now, this is effective. We create additional tools to generate a phosphorus recommendation for pastures. So what happened was, from both agronomic as well as environmental perspective, there were some areas that producers were just not getting the production they need, but also other areas where phosphorus was over-applied. What that change entail is, next please. Can we use, so I'm not focusing on these quick key questions. Can we use other diagnostic tools besides soil testing to predict pasture phosphorus requirement? And the answer was yes. We conducted a number of research trials, anything from lab, greenhouse, small plot experiment to on-farm experiments. So it was a tremendous effort, a lot of money involved, a lot of students involved. And the end result was we were able to change those recommendations. So now we feel much better in terms of identifying when phosphorus is needed. So that tremendously reduced the amount of fertilizer, pea fertilizer recommended for pastures in Florida. If any of you is interested in learning a little bit more, next please. We have 13 scientific papers. Like I said, if I come here and just talk about this, it will be just my opinion, my perception. But these results from these studies have been published, so my science peers evaluated, criticized, and now they are validated in the scientific literature. And a number of grad students and a number of extension and education activities associated with this. So let's transition from fertilization to solubility of phosphorus associated with different pea sources. And I just very briefly want to mention a very stunning, to me, is a stunning number that we are maybe perhaps ignoring. In Florida, Maurice, this morning he said we produce about 300,000 dry tons of biosolids per year. If you look at the FDAS stats for fertilizer tonnage, interestingly, the numbers are very similar. We consume about 300,000 tons of P2O5. P2O5 is not phosphorus. If you convert P2O5 to P, it's about 43% of that. So we use about 129 tons of phosphorus fertilizer per year. And then furthermore, if you look at the distribution of this pea fertilizer across the different counties in the state, and this is not the graphic that I'm showing you, by the way. You're trying to find where she's talking about that. I don't see that number. So this is just complementary information. About 21% of this 129,000, so about 80,000 tons of phosphorus is used in one county in Florida. About 21% of all phosphorus consumption is used in one county. Fertilizer, I'm not talking about biosolids. Can anybody guess what county is that? Orange. No, it's Palm Beach County. Palm Beach and Seminole, they use about 48% of the pea fertilizer in the entire state. So when you look at some very rural areas like Okeechobee County, Highlands County, where most of the cattle producers are, guess what the percentage is? 1%. So there's a stunning difference in how fertilized is used in just different counties. How that relates to biosolids, the meeting here is about biosolids, not fertilizer. But if you look at the, now I'm back to the slide. If you look at the y-axis here, this is water extractable P. Percentage of the total phosphorus in a P source that is water extractable. Why water extractable is important? Because water extractable is directly related to the likelihood of the phosphorus to become an environmental hazard. So in other words, the higher the water extractable P in the material, the higher the chance for the phosphorus to be transported. So if you look at this graphic, this is fertilizer, dairy manure, poultry manure, very small bars here for aerobic and anaerobic biosolids. So I'm using this as a visual. This is commercial fertilizer. How much available P is in the commercial fertilizer? So let's say this is 100 pounds of triple superphosphate. Now, if you use the same amount of total P, but using biosolids, the amount of available P or water extractable will probably be something like this. So you get the difference. There's much less available soluble P in biosolids versus commercial fertilizer. So we have to account for those differences when we make our nutrient management plans and our fertilizer decisions. Now, focus only on biosolids. There are different biosolids. This is a very generic term to define materials that are produced under different treatment process, and the end product also varies tremendously in terms of their properties and likelihood of resulting in an environmental problem. So this is a biological phosphorus removal cake biosolids. By the way, this slide belongs to Dr. George O'Connor, who spent his entire career researching biosolids. And I'm lucky that he's also one of my collaborators in some of the projects that we're currently doing. So there's a tremendous difference in the percentage of water extractable P in different biosolids material. Typically, the materials that undergo heat treatment or they add aluminum during the treatment process, usually that result in materials that contain less water extractable P. I suspect I'm almost running out of time. Switching to the next, kind of unrelated. I'm giving you pieces of the puzzle right now, and hopefully at the end I'm going to put the whole puzzle together. This is a visual representation how soil test was defined. Soil test, MELIC 3, that's the standard soil test in Florida. The values were defined based on agronomic responses. So for instance, in Florida, the agronomic response is every time the soil tests above 26 parts per million of MELIC 3 extractable P, that means that the crop that you are growing is not going to respond to any additional P. But this is for agronomic purposes. What this graphic is representing is increases in soil P and how the color choices here were not the greatest, but how dissolvable P in runoff increases as a function of soil test P. So there's a relationship between, there's a certain amount of phosphorus that can be retained in the soil. So soils have phosphorus retention capacity. Once that all the sites that retain phosphorus are full with phosphorus become an environmental hazard. So when we look at agronomic rate, that has nothing to do with likelihood of phosphorus to become an environmental hazard. However, if the soil test P increases over time, whatever reason is over application of biosolids or fertilizer, that phosphorus can become susceptible to losses. In our case, as Mauricio mentioned, leaching is the predominant pathway for phosphorus to be transported. So what I want to say is not all soils that test high for agronomic purposes will have this environmental concern. On the other hand, we can have soils that have medium levels of phosphorus, but because of some of the other characteristics, they can result in they can pose an environmental problem. So we usually, that change point, that phosphorus concentration in the soil that becomes an environmental problem is at least 3 or 4 times greater than the agronomic threshold. And there's some discussion, the new BMP manual for cow-calf operations incorporated that this concept. And that I mentioned that change point is related to the soil properties. Soil that contains more clay, they have greater nutrient holding capacity. Usually that inflection of the curve is a little bit higher. In other words, clay soil can retain more phosphorus than our sand soils. So the challenge is finding where exactly that change point occurs. So my point is, soil tests alone is not a good indicator. We don't know what the environmental threshold is. There are better tools to evaluate the likelihood of phosphorus to become an environmental concern. One of them, Maurice also mentioned in his presentation, is the Florida P index. We have one of the most elaborate P index in the country. I'm part of this multi-state group that we get together, different researchers from different areas, parts of the country. And by comparison, we are so much far advanced, and our recommendations are so much more stringent. The science behind our P index are much better than other states, but we need to implement these tools. Finally, very briefly, a study that we've been conducting at ONA with Biosolids for, now we're starting the third year of the study. This is Bahia grass production. The take-home message, don't worry about understanding every single bar. I can go over the bars with you if you're interested. But the message that I want to convey here is if you compare the orange bars, commercial fertilizer. These three materials here are different biosolid types. If you compare these three bars with commercial fertilizer, I don't know if I keep saying biochar. Fertilizer produce more forage in the beginning of the growing season. However, over time, fertilizer basically wears off because the nutrients are readily available for the plant. So as you continue the growing season, towards the end in the fall, fertilizer is gone. Biosolids, on the other hand, still continue to maintain that positive impact on forage production. So we don't care. We are not, some of you might not be forage producers, so you don't care how forage is responding. But, next one, please. If you look at the water quality data, this is nitrate leaching over time during the entire growing season. We have 3 years of data, by the way, and for phosphorus as well. So we have these drainage lysimeters that we collect water. This first collection was right after biosolids and commercial fertilizer application. You see the purple line and the blue line, these are inorganic fertilizer. So you see this was probably, I don't have the hydrology data here, but I suspect this was probably periods where the water table was near the surface. So you see these large pulses of nitrogen and phosphorus in the system right after fertilizer application. You don't see the same for biosolids because it acts as a slow-release source of fertilizer. So not only provides better crop responses, but also results in much less likelihood of that nutrient to end up in our waterways. I think I'll stop right here. Yes.
Or are you just going to yell?
You want me to do it from here? That's great. Well, it's good to be here. And I remember many years ago, first introduction to wastewater management, I was told there's good news and there's bad news about wastewater management. The good news is we've got the technology now to get wastewater to where we can drink it. The bad news is there's not going to be enough wastewater to go around. So anyway, 40 years ago, that went over a lot better. Okay, you've advanced to the first slide. I'm going to talk about the WAM model today. And this is basically a model to where we can actually go in on a watershed scale and assess what are the loading rates and how do things integrate throughout the watershed as far as providing loadings to the downstream. The WAM model is a Florida-specific model. It simulates surface and groundwater. It handles the nutrients. Also can do DO, chlorophyll A, and a few other things when we tie it to other models. It's GIS-based. It's a detailed field model is built into it, and it handles very complex flow networks, which is critical here in South Florida because we manipulate the water that doesn't flow naturally in many of our environments anymore. See how that magically works? I don't even have a flipper. The WAM model, this is a conceptual layout of how the model works. It basically tries to take into account everything that's going on in the watershed, and it starts at the field scale. And we model the field scale in great detail, and then we simulate what's going on spatially throughout the watershed, and then we move that water throughout the watershed down through whatever systems, reservoirs, canals, streams, whatever. So far, in the state of Florida, we've modeled about a third of the state using the WAM model. We've also used it over in New Zealand, and that was actually great fun. And also in South Africa, we've used this model. But you can see that a lot of the focus has occurred here in South Florida around Lake Okeechobee. And much of our focus has been down here using the WAM model, and you can see that actually the St. Lucie Basin has been one of the basins we've modeled. Here's the Okeechobee B-map layout. We've just completed modeling the entire Okeechobee Basin this past year. I should say recalibration of the model. We've actually modeled this a number of years ago, and we've updated that model. And what I want to do today is kind of give you a feel what that model can do for you as far as better understanding what's going on in the watershed. What the model uses is all the detailed spatial data that we have today. We have a very detailed land use coverages. We have structures, hydrology, hydrography, topography, all of that information. And we have that down to a scale that's very small. Matter of fact, we simulate the entire Okeechobee Basin on a 1 hectare scale. So we know and back up, based upon the accuracy of these coverages, we know how many nutrients are being generated at every point within the watershed. But it's only as good as what we know that land use coverage is. And not only the land use coverage, what are they doing on that land? Like a farmland, we don't really know if they're fertilizing to IFAS recommendations or not. But we make general assumptions about how that works. We have to have other information. We have rainfall obviously drives the model, detailed topography and the stream networks throughout the basin. The model simulates the complex stream network, so you can go to any point within the watershed, look at that stream, and we can know what the flows are and the nutrient levels on any given day. Soils, obviously soils are dominant, and when we look at the impacts, you can be treated, have the same land use, but have significantly different nutrient losses and water yields, either surface groundwater, based upon the soil conditions. The other thing that's interesting, like in the Okeechobee Basin, the areas in the green around the edges actually are areas that where the groundwater, most of the discharge is going to groundwater, but that groundwater is actually going out to the coastal basins, so they're not coming down the river. Most watersheds, the groundwater ultimately comes back into the stream system somewhere downstream as a spring or something else. One of the purposes of this model is really to look at BMPs, different practices, projects that are going to improve the nutrient conditions, reduce the phosphorus loads to Lake Okeechobee. The FDAX program, here's a picture of different projects they have within their BMP cost share program. And we try to include all of these in there so we have current conditions. Also, some of the special projects that are funded by the district or through other programs like the dispersed water program. I think there's a hybrid wetland program. Also the Kissimmee River restoration projects. we need to get all of those included in here and to properly represent it. Now this is I know you'd probably like to see this over for this area. The information is available, but I didn't happen to have it available today. There's whoops, I was just pointing. This is a figure showing the waste treatment plants distributed around the Okeechobee Basin and also the septic tanks. Department of Health actually has a very good coverage of where all the septic tanks are, and we've gone back and we've looked at this and done checks, and it's actually a good coverage. So all of that information needs to be included in it so that you're really seeing where the nutrients are coming from. Just to give you a feel that the model actually, I think, does a pretty good job. This is a prediction of the phosphorus levels coming out of the Taylor Creek Nubbin Slough at the S191 structure. So we actually pick up not only the magnitudes, but also the dynamics of how the phosphorus is coming out of the basin. So when we finish our calibration, we're fairly confident that we're doing a fairly good job representing the basin. Ultimately, what this can provide us is, on the left, well, look at the one on the right first. This is a prediction of the phosphorus concentrations that would be coming out based upon all the different land use soil combinations out there. So you can see the Taylor Creek Nubbin Slough area down by the lake is really a hot spot, and data has shown that for years, not a big surprise. The one on the left is the interesting one, in that this is the amount of legacy P. This is the phosphorus that's out there that is up and above what would have been out there in a native condition. And what this little analysis has done when we look at legacy P, there's about 190,000 metric tons of legacy P in the watershed. And if we went away today and just let it flush out at the concentrations coming out today, it would take about almost 400 years to flush the phosphorus out that we've put into the basin. So there's a big problem if you're trying to protect the lake. Ultimately, we've saturated a lot of these soils, and we've got to put in treatment systems and things like that. And one of the studies that we did back with Jack Siegel looking at pastures, most of these flatwoods, we found that with the grasses and pasture grasses, no phosphorus is the recommendation. There's actually adequate phosphorus. And the P budget work that we've done actually shows that we're still increasing this. We haven't turned the corner as far as actually increasing the legacy P that's occurring. Of course, biosolids plays a role in that. Wanted to just show that we did model the St. Lucie Basin here, and the focus of this was looking at BMPs on farms. We did a detailed modeling of 2 farms, small farms, a citrus and a pasture, and then we expanded those BMP information on up. Just showing what the land use coverages that we had within the model. You can see all this orange. It was still being mapped as citrus. Obviously, it's not all citrus anymore. So much of it has gone out because of greening and canker. Soils coverage. Next slide. Ultimately, we evaluated 7 different combinations of BMPs, and the green is showing what the nitrogen discharges were associated with the different practices. The one on the left is the base current condition. So ultimately, you can see BMPs, fertility and water BMPs, the red is for phosphorus, the green for nitrogen, that we're getting somewhere between 10 to 30% reduction. So BMPs are not going to get 80, 90% reductions that a lot of people are looking for, but they will provide some significant reductions. And the first one was for the pasture BMPs, and this is for citrus BMPs here. Ultimately, the model provides a picture of, based upon the land use, soils, and the conditions out there, the P loading coming off of the source cells. And that's every hectare out there, so you can kind of quickly see where your hot spots are and stuff. And the model does that for you. It does provide hot spots and that sort of thing. And this is for nitrogen. The first one was for phosphorus. So you can see the distribution of where you're getting the loads that are ultimately going to get out to the estuary. We built a secondary tool that takes the model output. It's called the load estimator tool that we're using in Okeechobee, which allows you to go to any point within the whole watershed, put in a project and see what ultimately that project's benefit will be at the lake, taking into consideration all the attenuation and everything that occurs throughout the watershed. This is just one of the analysis that was done. I know you can't read it, but ultimately you can come down to the bottom and come up with the net loading reductions that you would get associated with that. Kind of the last thing I want to show you, just one of the other benefits of having a model like this, you can predict into the future. This was for Rainbow Springs, where we went in and we modeled it. We did this a number of years ago. This was 2007, what would be predicted loads to the groundwater of nitrogen. Then we predicted forward what would happen if growth went on with no changes in land use practices. And then if you went on up to 55, it even got worse. So it clearly showed that if we just kept doing what we were doing, we were going to get in more and more trouble. And ultimately, here's a prediction of the nitrate concentration in Rainbow Springs over time. And the dots on there are the real data, and the lines are the predicted model data. And we were predicting into the future to what kind of concentrations ultimately be in the spring. And we did this back in 2008. We've gotten more data. The good news is that the concentration is actually starting to go below the predicted line, which means that we are implementing practices that are having benefit, which is a good thing. So there's a quick whirlwind tour of Wham.
Thank you, Dr. Botcher. Dr. Botcher had been talking to us about some of the freshwater systems, including the lakes, streams, and springs. We also, even though either one of them could talk to either one of these systems, they were gracious enough to split it up between the two of them. And so now we're going to have Dr. Janicki, speak a little bit on the estuarine systems in the coastal areas. And the questions would be, please talk about the sources of the nutrients in the estuaries and what are the trends you see?
Thank you, Gary, and good morning, everybody. In order for us to understand what the potential effects of biosolids might be, we need to put it in the context of what we know about what the other sources of specifically nutrients are, and I'm going to speak primarily to estuaries this morning. So, I've got that same magic thing. There we go. So, and we've talked about this already this morning, that one of the major, well, it depends on where you are, one of the sources of concern in terms of nitrogen in particular, but also phosphorus, are the point sources, including both domestic and industrial point sources. We often talk about non-point sources, the stormwater loading, and that the load of nutrients varies depending upon the type of land use, whether it be urban, agriculture, or in some cases even natural sources. Groundwater and base flow. It's not only the surface water runoff of concern, but also what's entering our estuaries through the superficial aquifer. It's an important consideration, especially given some of the issues associated with things like septic tanks. We talked a little bit about potentially reclaimed water. I'll go back to that in a second. But also, that may be the way in which the nutrients from biosolids may be entering our estuaries. The next slide, please. One of the things that I started working on many years ago up in the Chesapeake Bay area was the effect of atmospheric deposition. Well, you know what we found over the years that incredibly, because of the emissions of NOxs, especially from power plants and mobile sources. The effects of atmospheric deposition being wet or dry to estuaries is pretty significant. And in fact, up and down the East Coast, it accounted for anywhere between 20 and 40% of the total amount of nitrogen going into estuary was coming out of the atmosphere. So that's an important consideration. We've been looking at that explicitly here in Florida recently. So the question is, what's happening with biosolids? What might those loads be? And again, I want to put those, we have a lot of unknowns here, but in order to really understand what the potential effects are, we need to, again, put it in context of what the other sources may be. So how do you estimate loads? By and large, and Dal just talked about an excellent model that he's been working on for, we are two old men. You've been doing it a long time. And with each generation of it, as we gain information, we gain certainty in those model estimates. And that's part of the problem with modeling, is that there's a lot of uncertainty depending upon which model you're using. It's critical to make sure that there are lots of tools that are out there in that toolbox for modeling. It's very important to make sure that the model that you choose addresses the specific questions you need to ask at the right temporal and spatial scales. So, again, there are a lot of models that are out there, but you got to make sure that you're choosing the right tool for the right problem. The next slide, please. And again, that requires a lot, and as Del pointed out, some of the real critical aspects that need to go into a model, and typically those include things like land uses and soils and the amount of rainfall and getting the right hydrology. If you don't have those things right, you're never going to get those loadings right. So it's really important to have that good information. Monitoring to determine loads is problematic in many respects because of the cost associated with it. And the cost comes in primarily because in order to do a good job of assessing the load going into a water body, you need to make sure that you've got observations throughout a wide range of conditions, especially rainfall, which means you got to get out there a lot. And, having done these kinds of things many times, especially up in the Chesapeake Bay area, it's, especially for the people that work for me, kind of a pain to get out there when in the middle of a rainfall event. But those are the kind of things that you kind of need to do. The next slide, please. And again, as I was saying, a lot of it has to, it can be very costly, but make sure that we get that wide range of conditions when we do this. By and large, I think, from my experience, I think, granted, as I was saying, we're often pointed in the direction of doing modeling, but it also, and Dal just did a great job of showing how well his model estimations were fitting the observed data. A model is only as good as its ability to reflect the kinds of variability we see over time and space. And that's a real critical thing in choosing, again, the model of choice and doing those load estimates. So over the years, I've worked in a variety of places, but I'm going to talk about 5 different major estuaries that I've worked on in Florida, from Tampa Bay, Sarasota Bay, and Charlotte Harbor on the west, and Mosquito Lagoon in the northern part of Indian River Lagoon on the east. It's interesting when we use those 3 words, Indian River Lagoon, we got to recognize that, and I think Dwayne's going to talk about it later on. I mean, we're talking about a series, really, of lagoonal systems that aren't all the same. They have different problems, they have different characteristics, and it's really important that when we do that work, and when we talk about Indian River Lagoon, I would offer we need to be explicit when we talk about the area that we've been working on, and because they are quite different. So the next slide, please. So what I'm going to show you for these 5 estuaries, just a brief summary of where the nitrogen and phosphorus is coming from going into these estuaries. These are more recent loading estimates, and if we had done, and we've done these pies based on data from back in the 70s, it would look very, very different. And the major thing that happened, and I think hopefully most of you realize the success we've had in Tampa Bay. It's incredible. We have more seagrasses now than we did in 1950. And that's because of the yeoman efforts of the local governments in dealing with nutrient pollution in particular. Importantly was the passing of the Grizzle-Fig Act back in the late 70s, early 80s, that required any surface water discharge to Tampa Bay to be advanced wastewater treatment. That was the big kickstart in improving Tampa Bay, and you know, I've been telling my friends up in the Chesapeake, you know, you guys, you know, that's where you're going to get the good start, and I think they're finally doing that up there. And so today, the primary sources of both nitrogen and phosphorus are really coming from non-point sources, and that's really important. There are management actions that have been taken in terms of stormwater management to address these issues, but by and large, what we're talking about is non-point source being the primary source of nitrogen and phosphorus right now. Now, interestingly, much of the Tampa Bay watershed is in the so-called Bone Valley, so there's lots of natural phosphorus availability in the soils and the bedrock. But if we wanted to look at, for example, what's the proportion of the potential non-point source from agriculture, depending upon where you are in the watershed, of course, in Pinellas County, it's 0. But in Hillsborough County and Manatee County in particular, there's a fair amount of agriculture. And as a result, you know, ag sources to the non-point source may approach 20% of those non-point sources. Next slide, please. Charlotte Harbor, like Tampa Bay, and unlike Indian River Lagoon and Mosquito Lagoon and Sarasota Bay that I'm talking about, these two, Charlotte Harbor and Tampa Bay, are largely have large watersheds relative to the area of the estuary, which is a very important consideration when trying to evaluate nutrient loading. So in particular, for example, in Charlotte Harbor, you're probably aware that there are 2 major drainage systems that go into Charlotte Harbor, the Peace River Basin and the Myakka River Basin. Both of those have a fair degree of agriculture going on in them. There's also been a lot of build-out, but much of the area has either agriculture, mining, or is more natural. And so it's not too surprising that we see that the loading is dominated by the non-point sources coming from a variety of different sources. But you know, by and large, you know, understanding how stormwater management maybe will address those issues is an important consideration. The domestic point source, industrial point sources are relatively small, as are the septic tank loads. Next slide, please. Sarasota Bay is this lagoonal system, which is between these 2 river-dominated estuaries. And again, what makes these lagoonal systems interesting is that the area of the watershed that drains to the estuary is quite small. The other major characteristic to take into account when looking at these lagoonal estuaries is the connection to the ocean. Those 2 things are really what determine what happens in these systems. There are some areas that have a greater input perhaps from the watershed, but they may not be as closely connected to the ocean. So again, the consideration of the loadings and the responses loadings really depends upon those 2 characteristics. Now here in Sarasota Bay, similar to Tampa Bay, the Grizzle-Fig Act required all surface water discharges to go to advanced wastewater treatment. Many of those have actually been eliminated entirely in Sarasota Bay. And as a result, again, what we've seen in Sarasota Bay, as we did in Tampa Bay, excellent return of seagrasses in the system to the point that right now we're talking about protection, no longer restoration. In some cases, and the use of this is a model developed by my colleagues at Jones Edmonds, and it did take into account, it separated out the non-point sources from that due to irrigation, and you see that that's in that orange. I mean, and clearly, a lot of that irrigation is reclaimed water, so it is a potential important source. Especially with respect to phosphorus. The next slide, please. Indian River Lagoon. Now, where I'm talking about here, and be very explicit, there are 3 segments, if you will, of Indian River Lagoon that we've been working with Virginia Barker from Brevard County and her partners in a number of local municipalities that have been supporting the work that we've been doing on developing a revised total maximum daily load for that system. So there's 3 segments. Beginning from the north, there's the North IRL, then Banana River, and then as we go further south to what we refer to as Central IRL. This is a summary of the loading to all 3 that came up, that was derived by a model developed by Claudia Listopad and Harvey Harper. And interestingly, you can see that there's clearly a difference between the sources of nitrogen and phosphorus. It's being primarily dominated by very large portions are coming from surface water runoff, non-point sources. But the interesting one here is to look at that orange, and that's the base flow. And that was one of the things that really caught our eye when looking at these loading estimates, to make sure that we got the right numbers in the right places. Because how do you manage nutrient loadings if most of it is really coming in from base flow? You can manage the heck out of stormwater, and it may not make any difference at all. So having good information on this about the sources really is going to make our decisions about how to manage systems like this in the future. The next slide, please. And the last one I'll talk about is Mosquito Lagoon. It's the northernmost, well, kind of the northernmost portion of the IRL. And this is work that we've been doing with my friends from Jones Edmonds, working for Judy Grimm in Volusia County and some other local governments. In this case, we're developing a reasonable assurance plan, which is kind of a way in which stakeholders can avoid the TMDL process. But by and large, the process is very similar. You got to understand the loadings, you have to understand the responses in water quality, in which you come up with targets and evaluate allocations of those loads. So Mosquito Lagoon, interestingly, its watershed to the area of the estuary is really, really small. And in that southern portion in particular, there's almost no development. So the story that we see here is quite different, as we see from the rest of Indian River Lagoon. And it's, interestingly, that northern portion of Indian River Lagoon, of course, has seen some very, very significant impacts in terms of a series of algal blooms, one of which they call the super bloom. In many ways, we still don't really understand exactly what the cause of the initiation and the magnitude and the extent of these blooms, but luckily, Mosquito Lagoon has largely been has avoided those kind of issues, and we're going to be moving forward with developing that reasonable assurance plan for the local governments. So again, this gives you some idea that our understanding about various estuaries and where the nutrients are coming from. Understanding those, we can talk about management, and it's within this context, as we gain more information about biosolids, that we're going to make some meaningful decisions. And a quick shout out to my friends in DEP. They should be applauded for the development of that technical advisory committee that's going to look at biosolids. I think there's a lot that needs to be learned, and putting together this group in particular is the only way that we're going to be able to get to a point where we can confidently say we're managing those biosolids effectively. Thank you.
Thank you, Dr. Janicki. Now, Edie, one of the concerns that's been on the minds of Florida surface waters around these days, we've been hearing about the blue-green algae blooms in Lake Okeechobee and things like microcystins and things like that. We were just wondering, could you please discuss some of the issues related to these toxins and other health-related issues to biosolids, and are you aware of any potential secondary impacts from biosolids and algal toxins?
I'd be happy to, Gary. In case you're wondering why we're sitting like this, we had a meeting early on and we were trying to figure out how to spare you of death by PowerPoint. And the idea was to create a panel. I think we failed miserably. The only thing that we got out of this is we're all very comfortable. I'm going to be talking about some of the secondary effects of this nutrient loading that obviously sewage treatment is contributing to, and we've heard about them in various forms. So, we're all aware of what's been happening with the lagoon, going from what was once called the most biologically diverse estuary in the United States. We're now becoming an algae-dominated system, with 2016 being one of the most dramatic examples. Next slide. This is the brown tide that was just mentioned in the northern part of the lagoon, and which, by the way, is going on right now in the northern part of the lagoon, but had a massive, massive fish kill associated with it in 2016 due to a confluence of different factors. Next slide. This is unfortunately extremely timely because of the article that Tyler Treadway just put out in the paper showing the measurements that were just taken. There's microcystis, the same blue-green algae that was responsible for the lost summer of 2016, in the water again. And microcystin, its toxin, it has been measured there at 0.6 parts per billion, and that was Monday. They haven't got the measurements back from Wednesday, but it's looking pretty grim for this summer. Microcystin is a really interesting molecule. Next slide. It's a really tough little molecule. You can boil it, and it doesn't break down. It's still toxic. Next. And it's a hepatotoxin, which means it impacts the liver. Next. And there's been a lot of data, especially coming out of China, linking it to various forms of liver disease, and it's pretty strong data. So much so, next slide, that the World Health Organization has set the limit of microcystin in drinking water at 1 part per billion. And just to put that in perspective, 1 part per billion is 1 drop in a tanker truck full of water. So it's very powerful at very low concentrations. It is potentially lethal, and the limit for recreational exposure by World Health Organization is 10 parts per billion. There was a study that came out in 2015 from Ohio State University, next slide, where they looked at the correlation between algae blooms nationwide and the occurrence of non-alcohol related liver disease. Next. And any place they found high correlation, they put a red spot. You'll note there's a red spot right around Indian River Lagoon and Lake Okeechobee. Now, it's always important to remember that correlation is not causation, but it's definitely something that you want to be looking at pretty seriously. And so the question is, how is microcystin getting into our food web? One hypothesis, next slide, is it's probably being bioaccumulated. So the picoplankton is consumed by plankton, which are then consumed by small fish, consumed by medium fish, consumed by game fish, and it builds up and actually concentrates into the fish. So one hypothesis we're looking at is that high correlation might be because of the amount of subsistence fishing that goes on around the Indian River Lagoon. We've all experienced coming home from the airport at 2 a.m. and seeing fishermen on the bridges fishing. They are not recreational fishing. They are putting food on their tables. And so the question is, how much is that impacting these data? Unfortunately, we've gotten some funding from the Guardians of Martin County and the Francis Langford Foundation, so we're going to be actually starting to look at that. The other way it can be getting into the food web, next slide, is through irrigation. This doesn't concentrate it the way bioaccumulation does, but it has been shown in quite a few different studies now that food crops do actually take up microcystin. And one of the reasons that's particularly concerning here in Florida is because of the nature of our irrigation. Next slide. Part of draining the swamp in Florida involved putting in all these canal systems to drain the agricultural land, make it useful for agriculture, and also provide irrigation for those crops. But one of the things that we've been finding, next slide, with the Kilroys that are the water quality monitors that we've been using, is they're small enough that we've been able to put them into some of these canal systems. And one of the things that we found that's concerning is the occurrence, next slide, of something that we're calling cryptic blue-green algae blooms. And, you know, sometimes these go on over a course of a month or two during the summer. This is actually a recent one in the C23 canal in December for some random reason. We call them cryptic because there's no green slime at the surface, which means you're not even aware they're there. And it's not being tested for unless somebody sees the green slime. So that then could be being put on crops. Another concern is not just from the nutrient loading from biosolids, but also from this use of wastewater. Because one of the things we found kind of by accident, next slide, is we were doing a study where we were looking at the difference between communities that are on septic versus sewer. Next slide. We found a very high level of microcystin at this one community called Johns Island. And that was a little surprising because Johns Island is entirely on sewer. And some of the septic places that we were looking at didn't have nearly these levels of microcystin. And when we looked into it a little further, we found that they were using reuse water from the city of Vero Beach to irrigate their grass and their golf courses. Next slide. And it has, when we tested that water, it had higher levels of nitrogen in it and high levels of sucralose, indicating that it is coming from human waste. Another area of concern, next slide, is what's being called the new frontier of public health because of these contaminants of emerging concern. Next slide. These are generally getting into our waste streams from just our daily living, and generally at pretty low concentrations. Next slide. But you have things like, you know, birth control pills that pass through our bodies and end up in our waste stream, and pathogens and pharmaceuticals, many different pharmaceuticals, antimicrobials and then fragrances and preservatives and all kinds of things in personal care products. Highly fluorinated compounds are things like Scotchgard and Teflon, and they are very persistent in the environment, have been linked to cancer, thyroid disease, immune suppression, and low birth rates. Flame retardants are known to be endocrine disruptors. Microfibers is another one that's been showing up a lot lately. Even our artificial sweeteners, which you might think, well, we put them through our bodies, so they're fine, right? But we don't know what kind of impact that they are having on organisms in the environment. And there is a little data that's come out recently showing that they can have synergistic effects with some of these other contaminants of emerging concern and then become toxic in and of themselves. Next slide. They can be getting into our food web both from the biosolids and from the reuse water. There was a study that came out just a few months ago in Israel where they have to use a lot of biosolids and reuse water. And they were looking at carbamazepine, which is a drug used a lot for epilepsy. It's a very persistent one in the environment, and they were showing that it was taken up by food plants. But what was kind of interesting about that was they found that the reuse water was actually a much more concentrated source, that the biosolids actually acted as a source and a sink, whereas the reuse water acted just as a pure source. So when we're talking about these things, we have to be concerned about the fact that there are all of these chemicals now getting into our waste stream, and nobody is testing for them. They're in very, very small quantities, but we don't know what kind of impact that they might be having on the environment. When you see something like the next slide, which just came out last week, where there was this mass mortality of freshwater turtles. Freshwater turtles are actually pretty tough, and they noted that the dead turtles they were seeing were near sites where sewage sludge is allowed to be spread as fertilizer. So, what kind of impact might that be having? Next slide, which I think says question number 2, because we were going to do this as a anyway. Next slide. So my other question were some of these ancillary effects, and one that I just really wanted to emphasize because I think that ag needs to be aware of it is some data that's been coming out quite recently showing that the something like microcystin, a toxin produced by blue-green algae, which is in the water that is being used to irrigate crops, next slide, may actually be impacting not just what gets into the food, next slide, but crop yield. And this was a study that was done where they were looking at carrots and corn and green beans and lettuce, and looking at the uptake of microcystin, but they also found that at increasing concentrations of microcystin in the irrigation water, they were getting a much more reduced crop yield. So I think the top row is lettuce, and you see from left to right is the increasing concentration. The highest concentration there, I believe, is 10 parts per billion. And then the carrots, the same thing in the middle, and then the bottom is the green beans. And so just the number of beans and the health of the beans was reduced with the exposure to microcystin. This was such a good study, I figured I'd just end up with their conclusions from the study. Next slide, which I can't read on my own, so I'm just going to turn around and read it from here. Microcystin in irrigation water is a significant pathway for human exposure. Microcystin accumulated in crops and soil when grown with contaminated water. Crops lost their quality and productivity from microcystin exposure. Next, I underlined that one because, could you do next? Because that's the point I'm making here about the impact on crop yield. Microcystin from irrigation water persisted in soil after crops were harvested, and consumption of crops grown with microcystin-tainted water pose a high health risk. So this was from a paper published in Food Research International in December 2017. And with that, I will close.
Thank you. Let's see if I can't maybe kind of wrap this into a big bundle here and just kind of talk about how this relates to our total maximum daily loads and what the impacts of biosolids have been from some of the modeling that's been done and the past data that's been collected. I totally agree with Dr. Silviera that we ought to be doing this not based on emotion, but let's look at what the studies say and let's see what the data says. Slide. Okay, this looks busy, but it's not that complicated. You got 3 circles. There's 3 places where you can do something about nutrients in surface waters. One is a stormwater program, and there's both state programs and there's local programs. And every local elected official here, you have an engineering department that does your stormwater programs, and you've been spending a lot of money since about 2000 or so to try and, when you're retrofitting your facilities, to try and do the additional best management practices for urban areas, and you've been spending a lot of money to do it, and you've been making a lot of progress. I also want to look at, show you down there when you're looking at the algal blooms, this water that we have in our estuaries, whether it be a lake, in-river lagoon, or anything else, it's like soup. There's only 4 things that you need to get a bloom going. You need water, you need phytoplankton, you need nutrients, and you need sunlight. If you've got those 4 things, you've got some soup. Now that soup can be anywhere from broth, which is not bad. It can be soup. It can eventually be stew, depending on how much nutrients are in there, or it could end up being a pretty thick chili. And that's what we have when we have the hyper-eutrophic systems. But what it causes is is those 4 things: sunlight, water, nutrients, and the plankton. There's 7 things that bloom out there. You got blue-green algae, brown algae, red algae, diatoms, dinoflagellates, and there's a water mold out there. It's called Phanomyces. And there's different species of them. And it's like, who really cares? Every time we get a bloom, it's like, well, what was it? Oh, it's Cryptoparadidianopsis. Oh, well, what was it this time? Oh, it was a Phanomyces. Well, that's interesting. We got to study that. Why was it a Phanomyces this time? Was it because what caused it? And you'll hear things like, well, what caused it was, 10 days of sunlight, or the temperature changed, or the salinity changed, or something like that. That's not the cause of the blooms. The cause of the blooms is that you got water, nutrients, phytoplankton, and sunlight. What you're talking about is what initiated the bloom. And it's like, who cares? That's a great analysis and all like that, but the point is we don't want the blooms to occur anymore. You can do all kinds of analysis. You can take Jim Morris's name, rearrange the letters, and it comes out a phrase of Mr. Mojo Rising. But, I mean, who really cares about that kind of analysis? Because that's not what's causing the blooms. The blooms is too much nutrients in the water. Now, the other thing that we have at a local level is you got stormwater programs, you got utilities, and that's where you're taking, sometimes you're leaking and failing septic tanks, converting them to central sewer, and you put it in the utilities, and you come out with biosolids, which now we take those biosolids and put them out on the land where now it can be washed right back into the swales, ditches, and canals and end up right back in the water. So how do we deal with this loop? And let's not mince words here. It's waste. It's human a biosolid waste. And you say, well, how do you call it waste? Well, if you don't put it on land, where do you put it? You put it in a landfill. So we can mince the words all we want, but it's a waste. And we need to deal with that waste somehow. And are we dealing with it in the right way? And what makes this whole system what fuels the whole system is nutrient import and export, okay? And nutrient import, simple. You got food, fertilizer, and biosolids. That's all you got for the imports. Those are the 3 things. It's not that complicated. There's also, when you're exporting things, whatever you're exporting is what comes out of your agricultural products. So you got citrus, cattle, row crops, biosolids, okay? That's as complicated as it gets. So where are we with that nutrient import versus our nutrient exports? Next slide, please. Now, research has shown, this is according to IFAS, University of Florida, research in Florida has shown that Bahia grass may produce satisfactory without phosphorus fertilization. We heard the doctors talking about how red their models were showing with how much phosphorus is out there. Florida has got a lot of phosphorus. We've got a lot of legacy phosphorus. It's been out there for a long time. It's been accumulated for a long time. We mine it out there in the central west portion of Florida. Next slide, please. Dr. Botcher was talking about his analysis. He said it would take 350 years to wash out all the phosphorus that's in the Lake Okeechobee Basin. Now, they can spin that a little bit, and what the agencies have done and is basically say, yeah, well, phosphorus is not that mobile through the soils. Some scientists will say, well, okay, let's use a transport of 50% of the phosphorus through the soils to surface waters. And then some people will say, okay, how about maybe it's as low as 12 to 25%. Well, even if it's as low as 12 to 25%, it would take 23 to 57 years to wash all that phosphorus out of there right now to meet the TMDL targets for Lake Okeechobee. Mr. Busher, how old are you?
I don't remember, I'm 59.
59? You're going to be dead before you need any more phosphorus out there, just in general. Good thing. Next slide, please. Okay, so this is some analysis by Harvey Harper. He was looking at where is all the fertilizer being used right now. And as you can see, it's mainly in farm. 81% of the nitrogen fertilizer in the state of Florida is on farms. And 89% is on phosphorus for fertilizer on farms. So what we really need to be doing is we know where the major amount of nutrients are, and that's not a bad thing. Agriculture needs fertilizer. But what we need to do is make sure that we don't over-fertilize. When you're looking at, everybody did, a bunch of counties did their landscape ordinances. When you did your landscape ordinances, you were probably fighting tooth and nail to get those things passed, and you're talking about 6% of the nitrogen and 3% of the phosphorus. And I remember going through those, and it was pretty painful. And it's like, well, that's fine. We're dealing with mice over here when there's a 5,000-pound gorilla sitting right next to the pile of bananas, and we're wondering who's eating all the bananas. Next slide, please. Now, agriculture has been implementing the BMPs, and they've been compliance. Of course, everything that's been promoted in BMPs is trying to limit some of that nitrogen and phosphorus. And if you're a farmer out there and you sign up for the BMP program and implement the BMPs, there's a presumption of compliance that you're complying with state water quality standards. Now, it's not backed up by any monitoring or anything. You're just assumed to be in compliance. And I don't know if that's a good thing or bad thing. Make your own decision on that. Next slide, please. And so they have been signing up for these BMP programs, and since 2003, there's been 22% less nitrogen bought in the state of Florida and 33% less phosphorus, which is a good thing, because that's saying that agriculture has been implementing these BMPs and they're using less N and P. But the problem is we're still not far enough. That's a good start and that's a good thing, but we need to do better, and here's why. Next slide. There was analysis done from 2006 to 2006 to 2015, 10 years of data. And they're saying, how are implementing these BMPs working? How are we doing in the watersheds? And what they found out was from that 10-year period, they could see no sites with any decreasing trends in any parameters. Now, that'll tell you that we need to do more, but that also tells you there's a lot of legacy, both phosphorus and nitrogen out there. And so, again, we can't let up. We're making some progress, but we still have a ways to go. Next slide. Right now, or when they did the modeling analysis for Lake Okeechobee, the total phosphorus imports were twice as much as the exports. And the total nitrogen was almost 3 times. You're importing 3 times the amount of nitrogen than what you're exporting. So you got a cup, and you're putting 3 marbles in, taking 1 marble out, it starts filling up with marbles, whether it's 2 to 1 or 3 to 1. And so we need to see about how do we get those numbers, that efficacy, closer to 1 to 1. What I also found out in this analysis was about 12% of both the nitrogen and phosphorus imports were ending up in the surface waters. So when you bring the material in, about 12% of it is going to end up in the surface waters. Next slide, please. Now, septic systems. You know, we always have this argument, is it septic, is it that, you know, what's going on? Nitrogen migrates through the soil column, and it can make it into surface waters. Next slide. Phosphorus is attenuated and stays next to the septic systems. So you're not getting a lot of phosphorus into the surface waters from septic systems, because once it's down 3 to 9 feet in the vadose zone, it kind of stays there, and it's not mobile at all. So when you're seeing high concentrations of phosphorus, it's probably not coming from leaking septic systems, it's coming from fertilizer. It's got nowhere else to be coming from. Next slide. Here is our St. Lucie estuary area. We got Port St. Lucie, all the urban going into the estuary and around the lagoon. Next slide. It's about 6%, estimated 6% septic tank loading into the St. Lucie River, even with all those houses and everything. And it's because we've got a large agricultural watershed, C23, C24, C44, all also draining into our estuary. But how does that compare like nationwide? Let's go to Chesapeake Bay. Next slide. Chesapeake Bay, you got Baltimore sitting out there. Next slide. They're about 8%. Total load from septic leaching is 8%. And as was mentioned before, in the Chesapeake, I believe Dr. Janicki brought that up, they still have 29% of the nitrogen load coming in from direct wastewater because they still allow direct discharge of wastewaters from their wastewater treatment plants to go into the bay, where we stopped back in the mid-90s. Next slide, please. So, as Maurice was talking about, they have removed the amount of Class B biosolids because, remember, state statute just recognizes Class B biosolids as a biosolid. So you look around there, look around Lake Okeechobee, and you don't see any sites where any Class B biosolids are being applied. But now let's go and take a look at the AA. And remember, the AA is twice the amount, where the Class B is 100,000 dry tons. Class AA is 200,000 dry tons. Next slide. And when you have Class A, there's some kind of Jedi, Obi-Wan Kenobi mind control thing where we say, Class AA is not biosolids. It's not biosolids. It's fertilizer. It's fertilizer. Okay? But so let's look where it's being applied. There's where the AA are being applied, or the counties of AA, where it's being applied. And remember, it's twice the volume. Next slide. Put the two together. And when you hear things like 82% of the lakes in Florida are impaired for nutrients, you kind of get an idea, well, maybe we ought to look at this a little bit. Maybe we could do a little bit better. Next slide. So, how is this being affected as far as the BMAPs go? There's been 25 adopted BMAPs. Next slide. Here's the Caloosahatchee. Now, the Caloosahatchee is just based on nitrogen. And the green bar over on the left-hand side, that's where we kind of started out around 2000. And the most recent data shows that we're on the right side. Don't worry about the numbers. But the point is, we got to go from that right side green line down to the blue line, which means we got a lot of places. All that urban retrofitting stuff that you municipalities are doing, you got to do more because we got to get down there. Ag, all the things that you've been implementing in BMP, somehow we've got to come up with some way to get these nutrients from that left-hand side bar down to blue. Next slide. We'll go through these fast. Here's Lake Okeechobee based on phosphorus. Look at where we got to go in Lake Okeechobee for phosphorus. Next slide. Here's where we are in Banana River. The blue line is nitrogen. You got to get down to the red line. The green line or other blue line, you got to get down to the red line for phosphorus. Next slide. Here's where we are in North Indian River Lagoon. A ways to go. Next slide. Central Indian River Lagoon. We got a long way to go. Next slide. St. Lucie River Estuary in both nitrogen and phosphorus. We've got to do something. We've got to come up with something. We've got to pull some kind of rabbit out of our hat somehow, try and limit these nutrients. Next slide. Now, what are these costs? When you look at what does it cost to remove a pound of phosphorus or a pound of nitrogen from these two different systems, look at in ag, it costs you $130 a pound to take out total phosphorus. And the way that you do that is shallow water, stormwater treatment areas that hold water about 4 feet. That fluctuate the water. You can't hold water any deeper than 4 feet out in the ag areas. And that amounts to about $26 a pound for nitrogen. But look at the urban, the cities, the incorporated areas. Here's what your BMP costs are. Almost $6,000 for total phosphorus and about $2,000 for total nitrogen. That is amazing. Now, let's take a look at right now. Y'all remember that we're not supposed to have any more phosphorus in the Lake Okeechobee drainage basins because it's pretty well saturated. We don't, bush is going to die before we need any more. To this year, we're putting 1,000 tons of phosphorus in the Lake Okeechobee area just from Class AA biosolids. 1,000 tons. That means, and what we hear, about 12% of that ends up in the surface waters. So that's 120 tons of phosphorus that's going to be ending up in the surface waters. That's 240,000 pounds of phosphorus when we don't need another pound, and we're trying to figure out how do we reduce the amount of phosphorus going into the lake. When we treat our wastewater and create the biosolids, we have it contained. We have it up here, we have it at our facilities, we have control of it. Right now what we're doing is taking that where we have control, and this isn't generated by agriculture, we're taking it and flinging it across the land where it can be washed off through the ditches, swales, and canals right back into the surface waters. That's what we're doing with it. Is there a better way of doing this? And that's what we're going to be looking at this afternoon, is what some of those possible alternatives are. And so with that, I'll conclude. Oh, wait a minute, wait, I got 2 more slides. Next slide. Oh, this is, you elected officials, this is what you're going to be seeing in about 2 weeks. Before your commission meetings, there's going to be a bunch of people having a Howard Beale moment on you. And what you don't want to be showing them is, next slide. Oh, this is what you do want to show them. We're going to be looking at alternatives. Here's what we need to do. We still, municipality, state, we still need to do our stormwater programs. We still need to convert failing septic systems. And agriculture needs to raise its game a little bit to see what we can do about that efficacy. And I'm saying FDACS, FDEP, IFAS, come on, man. Let's see what we can do to try and get that 2-to-1 and 3-to-1 a little bit better, so that when the Howard Beales show up before the commissions, next slide, you don't have to be sitting there saying, oh, we don't know what's happening. We've never heard about this stuff. What are you talking about? It's the Army Corps of Engineers, okay? So thank you. What do you want to do? Who's going to announce lunch? Oh, wait a minute. Couple of questions? Okay, we got time for a couple of questions. Two questions?
Gary, you kind of implied that the reduction in total nitrogen and phosphorus in Florida was due to the best management practices being effective.
Yes.
But a lot of your other data doesn't reflect that. I mean, you still are showing 81 and 89% is farm-based fertilizers. The report you said so there's no decrease in the trends, and imports are still exceeding exports. I would say that total reduction is more due to the fact that so many tens of thousands of acres of citrus are now out of production. But the remaining farming going on is still not, these best management practices aren't working because they're not being monitored.
Well, that's part of it, but I mean, they are working and they are making a difference. They're not going far enough. And you can't really say because there's been no change that it's because the BMPs aren't working, because you got to remember there's still legacy phosphorus out there. When the doctors were talking about it'll take 350, somewhere between 23 and 350 years to wash all this phosphorus out of there, there's legacy phosphorus that's just coming out all the time. So even if we were at zero today, it'll take a little bit of while to wash that legacy nutrients out.
I'm just saying a 20% reduction in total fertilizer in the state of Florida is probably attributed to the 60% reduction in the amount of citrus in operation.
Man, that it could be, but even though that's could be a fact and a statement and a good thing, the bottom line is where do we go next to try and reduce those nutrients that are going out there? And I'm saying we're in control of our biosolids. What can we do about it? Yes?
I read in this morning's Palm Beach Post that the chief cause of nitrogen causing the blue-green algae bloom in our estuary in the St. Lucie is from septic tanks. And I'm not defending septic tanks. I think we need to convert the bad ones, and I certainly think we need to stop making the problem worse by tightening the permitting on them. But I didn't hear or see anybody there on the panel say that the major cause of nitrogen in the St. Lucie estuary, the southern end of the Indian River Lagoon, is from septic tanks. Did I miss something?
Well, actually, I did do a slide on that that talked about, there was a study that was done, I believe it was done in 2013. It was conducted, it originated at FDEP. It was done by independent scientific sources, and what they said was in the St. Lucie estuary, it was at 6%. You may want, Maggie, you might want to talk to Gary Goforth about that, because I used his slide. That's Gary's slide, and he's referencing 3 different studies that all indicate that it's around 5% in the St. Lucie. That's cattle, corn, row crops.
You're measuring the amount of cattle and corn is going on.
Yeah, right?
Right, and it's also the discharge of the water is taking it. That's one of the exports.
And they measure. Department of Agriculture measures what the crop production is in county by county. Yes.
Maria, you talked about, the phosphorus, and I was glad Gary talked about it not being necessary for the Bahia grass, but with other crops too, and even with the grasses, with the high pH that we have here in most places in Florida, that means that the plants cannot draw up the nutrients as well, and don't they need to lower the pH in order to use less fertilizer?
Could everybody hear the question? Okay, correct me if I'm wrong. The question was relative to having high pH in the soil, whether it will be a better strategy to lower the pH, so the phosphorus in particular will be more available to some of these crops. All the nutrients. Well, let me just clarify. There's an optimum pH for certain crops. Most soils in Florida, a natural soil, uncultivated soil in Florida is extremely acidic. It's a 4.5. So if the soil has high pH, it's probably due to management. Something happened in irrigation that caused the pH to be extremely high. That's not a natural. We have a couple alkaline soils in the state, but in general, our soils are acidic. Nutrients, any nutrient, nitrogen, phosphorus, anything that's added, plants will have a better chance to utilize, and therefore decrease the likelihood of that nutrient to be transported if the pH, the soil pH, is within that adequate range. So yeah, you're absolutely right. The first step in maintaining the nutrients within the root zone is by correcting the pH. This is correct.
Okay, I'm sorry, but we're about out of time right now. If you can get with any of the panelists or whatever and ask any other questions that you have. All this talk about biosolids has made me hungry. So let's go get our victuals.